Okay, smile. You're all on candid camera. Okay. All right. Captured for posterity as to how you participated in this course, right? Okay. Um, so I was just about to begin saying, Mihir asked me whether I'd be beginning with basis functions today because he's planned a breakout session regarding basis functions, and so appropriately enough, we'll do basis functions, regression with basis functions in today's lecture. Last lecture, I introduced regression in some simple way, and we talked about polynomial regression, where we are using powers of x, and there we are trying to discover the weighting for each power of x that forms the function that maps input to the output. And I mentioned that polynomial regression is not very useful outside of a single input variable. Today we will look at something more general, where we use linear regression, where we figure out weights for the raw input or waits for some kind of a basis functions as which replace the function values. Like we looked at x squared, x cubed, x to the power of 4, like that. Those are all polynomial. Instead of that, we replace it by some basis functions, phi1 of x, phi2 of x, phi3 of x, which is a generalization of that same idea. And that is much more powerful. We'll look at that for regression. So let us begin with one example of regression. And you'd be surprised that every time you're doing a Google search, you might be invoking the result of a linear regression problem. So you're typing in something into the Google window and asking you to find the relevant pages. And how is that being done? Of course, you can say, well, it's done by page rank, right? You typed in something. Let's say I was today looking for a case for a cable. And I was typing in, case for cable. When you have a lot of wires, I just want to put them in some kind of a casing. And I was looking for that, and it took me to the Amazon site or some other cable companies that sell these kinds of things. $5 a foot or something like that. They'll sell you these casings, plastic or metal or something like that. And of course, you can say, how did it get to that page? Of course, one famous solution of Google is what Sergey Brin, one of the founder, and Larry Page, the founders of Google, they first came up with the idea called page rank, right? Which is the page that most people go to when they are looking for a casing for a cables. And they might say, oh, this company is the one that seems to sell a lot. It's very popular, so it takes you there. So that is just one feature, if you will, is page rank of that site. But there can be many other features, if you will. And the goal for the machine learning program that was used to design that search engine would be to take a number of different features, only one of which is the page rank, but others may be in terms of what importance does that page give to what you typed in into the Google search box, because that's exactly what is appearing on that page. I typed in, cable cover, outdoor cable cover, if I typed in, and you find on some page exactly outdoor cable cover, and this is exactly what this page is about, says, okay, that's got to be a good page because that seems to be answering my question. So there's another feature, how well that destination page captures what I'm looking for, how the whole world regards a page that was the first one page rank. And it could be other measures such as location could be something, where it is located compared to where you are. It might say, okay, here is the local Home Depot that's selling that. And it says, okay, we know that you are in Buffalo and here is a Home Depot nearby, and it's telling you that's something. Okay, there could be several of these features, several hundred features. And so the regression problem would be to figure out what is the weighting for each of these features. And the weighting should take you to a value for that. So a particular page gets a value. And so it would be looking through all the pages. Of course, it's got the entire World Wide Web available, and maybe that's been pre-processed to some extent. And it would like to rank them for you and say, hey, here is the page that is most relevant to you. Here's the second most, third most. It gives you the ordering. And if I click on, I'm feeling lucky, maybe it goes to the very top choice, and there you have it. So the problem is really one of linear regression, which is being solved, but it has figured out all the weights for you. The weight would depend upon the input and the page. And of course, it needs to go through a machine learning process to figure that out. So let's assume that at some early point of time, when they set up the Google search engine, they would give examples of, for this query and for this page, the match is it very good, or is it not so good, not at all good, or somewhere in between? Don't know. So some kind of scoring is given. So you would have a training set which would take you from a combination of what you type into the search box and what the page contains and what is the score associated with it. Is it a high score or a low score? And such a training set would have to be used. And a machine learning program, a linear regression program, would go about figuring out what each of those features values are. So I just wanted to give you a simple example of linear regression, how linear regression can be useful. And it's not a classification problem. So it's not a problem where it is telling you that is, like the top 10 choices. No, it gives you almost an infinite set of pages, and they're all ranked in terms of some kind of value that's coming out. So that's called the learning to rank problem, letter problem. And that is a regression problem. Okay, so I just wanted to motivate you with regression. So let us then formally go to our lecture today, which is linear models for regression. Okay, there we are, linear models for regression. I had another lecture on the learning to rank problem. I don't think we have the time to go over that part of it. It's on my public web page. If you're more interested in that Google search engine, how regression is used, you can go take a look at that. That's a very specific application. We are going to be talking more in general terms about what is linear regression. And I was just trying to motivate you, saying, why should we learn this problem? Okay, where is it useful? Okay, so we're going to look at what is regression. We already saw polynomial curve fitting with scalar input. We saw it on Monday's lecture. And a more general solution is linear basis function models. And then we look at maximum likelihood and least squares. I introduced that also last time. And we discussed stochastic gradient descent and then regularized least squares. So all of these topics are there. That's actually quite a bit for one lecture. Let's see how we do on this. So the regression task is a supervised learning task. That is, we have some input-output pairs available, and they're shown here mathematically as a data set of known inputs and outputs, x1, t1, xn, tn. All right. Xi is an input, possibly a vector. So X is a vector. I just mentioned in the learning to rank problem, we can have large vectors to solve the problem of finding the web page we want. And associated with it is a score TI, is in the web page example again, how good is the match, and XI would be the feature, which would be whatever be the input feature vector is. In the learning to rank problem, that XI would consist of the features associated with the pair of the input query and the particular web page. And based on the matches between the two and so on, you would construct a vector. And so the problem is to map the XIs to TIs for an unknown XI that you have input. You've not seen it before. The data set, of course, has XIs and TIs, which you know the values. Goal is to predict T from X for some future test case. And we are not trying to model the distribution of X. We just, in a sense, it's not a generative problem. It's a discriminative problem in that we're just trying to predict something rather than construct a distribution of the input. And we don't expect the predictor to be a linear function of X. That's an important thing. So ordinary linear regression of inputs will not work, and we need to allow for a nonlinear function of X. And we don't have a theory of what form the function will take. So that is the general problem. Here is an example problem, 50 points generated from a one-dimensional problem with X uniform from 0 to 1. So X-axis going from 0 to 1. Y is generated from the formula Y is equal to sine of 1 plus X squared plus noise. So there is a function sine of 1 plus X squared. Presumably the solid curve is that function. But we not only have that function, but we also have noise as a normal 0.03 squared. That's the variance and distribution, or the standard deviation of 0.03, and a noise-free true function, and the data points are shown. So we are given all these noisy points, and the task is to figure out some kind of a mapping from input to the output, so that in the future, when we give a new input, we can say, here is the output for that. Okay, here is another example of regression. It's another intuitive example coming from standard statistics. Expected claim amount an insured person will make used to set insurance premiums or prediction of future prices of securities. So look at the
Hello,
data.
Professor.
Yeah.
Sorry to interrupt, but the students are having difficult time viewing the numbers. So can you make
You
the
want me to enlarge it? Okay, right. They're all small numbers. All right, good suggestion. Let me just put it into slide show mode. Okay, all right. Much better now?
yes, Professor?
Okay. So we are looking at expected claim amount an insured person will make. All right. So let's say we have a data set like this. Policy holder age 60 plus, 50 to 59, 40 to 49, 35 to 39, 30 to 34, 25 to 29. This is a data set. And the average claim made is $186 for somebody who's 60 plus, 186, 184, 171. Now it's going down. But certainly it keeps going up here. For a youngster who's between 17 and 20, the expected claim is $224. So we have an interesting curve here. As the age increases, the amount keeps decreasing, and again slightly goes up after 40 or so. I guess old people again may not see well; they might run into accidents, and young people are maybe novices in driving or careless, and they also get into accidents. So here, so the premium is high for very young people, right? Which you might know already. You probably are falling into these categories where your premium is higher than for somebody who's older. And then, of course, there is a standard deviation for this also. And so the premium is going to depend on the policyholder age. It also is going to depend on the vehicle group. A, B, C, D are 4 groups of vehicles. Maybe like an expensive vehicles are D, and a cheap vehicle is A, right? So it's $178 to $239. And the insurance premium is going to depend also on the vehicle age. If it is brand new, 0 to 3, it is $281. 4 to 7-year-old is $255. 8 to 9 years old, $192. So an older car is cheaper to replace. So you can think of it like this. The insurance company knows about all these things. Policy holder age, what was the claim? They have a data set, so they can look at it and they know depending on what kind of car you've got and what the age, so they know all this. So then and you come in saying you apply for automobile insurance to the company and say you fill in the form saying how old you are. Maybe let's say you're 25 and you have chosen a vehicle group B, and you have chosen your car is not brand new, but it's 4 to 7 years old, and they have to tell you what's going to be your premium, right? So you can say this is something like a regression problem where we have values and for each combination, you have some kind of a premium that has been set in the past. All right, we have broken it down into individual variables here, but in general, you would say for any some combination. They've had people X, Y, Z, and so on. So X was this old, this was premium, this is what we charged, and so on, like that. And so using these tables, they would have charged them at some point. And so they would want to use that to make a prediction for you. Okay, so regression is to predict a numerical value t given some input, and the learning algorithm has to output a function f r sub r super n to r, where n is the number of input variables. So you have to map a set of numbers, a vector of numbers are in n-dimensional space. Like you would have all those three, and you're mapping it to a single value. And so that is a regression problem. Of course, the classification is if the value is a label. In this case, in the case of automobile insurance, it's actually a value. You'd like to get a number like $187.55. That would be a regression problem. It will not be a classification problem. Ordinal regression is we have discrete values, but they're ordered categories. So in the sense, if you have values that can be ordered 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., and there is some ordering, natural ordering that exists, and it's called ordinal regression. But in general, your regression, you have an infinite set of values, and in classification, you have a discrete set of values that need not be ordered, like they could be classes. Okay, we just saw what is a polynomial curve fitting with a scalar. With a single input variable, we saw what polynomial curve fitting was. Yx comma w is equal to w0 plus wn(x) plus w2x squared. This is called polynomial curve fitting. We saw this example last time, how we could learn w from the training set by setting up a error function e of w and computing the derivative of that and so on. And setting that equal to 0, solving for w. And so this shows a second order polynomial model, fourth order polynomial, sixth order polynomial for some data here, some data set we saw it, we had seen earlier. And we have the true curve is this blue line here. It was something like, we saw that 1 plus, there was a sine of something, right? 2 pi we had. So plus some noise. So if you use a polynomial fit for this problem, I guess you would get second order polynomial. I suppose this, the gray one is the original data, and then we are adding noise to it to get the dotted points, and blue is the second order polynomial model, we say. And when we use a fourth order polynomial, that seems to allow for a finer, this almost looks like a parabola here. Second order defines a parabola. You're restricted to parabolas or some variants of that. Here we have something that is not quite a parabola. It's got some finer variations. The fourth order polynomial. A sixth order polynomial is undulating all over the place. It's going all over here. And maybe it's fitting the data even better. But we saw earlier on that maybe it doesn't generalize well because the real data came out from this gray data. So if I give you a new sample, it might be really off because look at that amount of error you might have here is quite high, right? So on. So this is the result with a polynomial basis function. So we are now looking to do a regression with not just one input, like in the polynomial regression, but with multiple inputs. We want to predict the continuous values of a target variable t given value of d input variables x1 through xd. And t can also be a set of variables, multiple regression. What about the output? Does it have to be scalar? If you have 2 or 3 values you're trying to predict, then it's called multiple regression. In the example of the automobile driving, I think we saw this example before, where the input to the automobile is what is seen by the camera, which is a high dimensional input, and that has to control 3 outputs: the steering, which is a continuous variable, the brake, which let's say is a continuous variable, and the accelerator, which is also a continuous variable. So if you're going to solve all these 3 problems simultaneously, which we have to, right? So that would become a multiple regression problem. So there again is an example of regression and multiple regression. So this regression problem occurs all over the place. When we talk about machine learning, we largely think of it as a classification problem because that's kind of easy to define, saying is it a cat or a dog, that kind of a thing. But you see, these problems, regression problems, are also equally important. So you can think of machine learning not just as a problem of classification, but also one of regression. And we work with these things. So we're going to do linear regression, which are linear functions of adjustable parameters. Specifically, linear combinations of nonlinear functions of the input variables. We just said linear means you're going to draw straight lines. How do you get nonlinearity, which is required for complicated data? We get nonlinearity by taking nonlinear combinations of linear functions of input variable, nonlinear functions of input variables. So we take powers of x, but they are going to be multiplied by weights and added as if it was linear in the weights. So polynomial curve fitting is only good for single input variable, cannot be easily generalized to several variables. So the kind of linear regression we are going to be working with is this one. The simplest version is a regression with d input variables. Supposing we have d input variables corresponding to whatever we are measuring. And the output is W0 plus W1x1 through WDXD. We can write it as W transpose X, right? We learned about vectors. So we're saying you have given me a vector X with D inputs, then I'm going to try to find a vector W. When W and X multiply with each other using a scalar multiplication or an inner product, we get an output value, which is exactly what we're looking for. So it's called linear regression since the linear function of the parameters W0 through WD, and the input variables are X1 through XD. And significant limitation, since it's a linear function of the input variables, it's not very complicated. All you can draw in X space of this is going to be a straight line. There is not even powers of X involved here. So it's going to be just figuring out the best possible straight line to fit the data, which is not very appealing. So more generally in a multidimensional space, it becomes finding a regression plane. In this example, we have 2 variables, x1 and x2. And then there is here, look at a table here, x1 and x2, the values are like this. And then t is the target variable, the values look like this, t. And then here's a plot for the values t corresponding to values of x1 and x2. And linear regression would be the problem of finding a best possible plane to fit these points. That's still linear regression. And that plane will have an equation of the form y is equal to b plus w1 x1 plus w2 x2. So the problem is to find w1 and w2. So this would be linear regression if you directly work with the variables x1 and x2. We may now want to have much more complicated formations of the data rather than being able to fit with a plane. So here comes basis functions. In many applications, we apply some form of fixed preprocessing or feature extraction to the original data. If the original variables comprise the vector x, then the features can be expressed in terms of the basis functions phi j of x. So we are saying that we replace the x's with some function of the x. For example, the powers of x it could be. By using nonlinear basis functions, we allow the function xw to be a nonlinear function of the input vector x. Okay. So what we are now going to say is, instead of linear regression with some variables x, we do linear regression with so-called m basis functions. So we say that we replace the x's with a bunch of functions phi j f x which run through j equal to 1 through m minus 1. And you see we're taking this huge vector x and replacing it with some other vector phi j, which is a function of that x. And the dimensionality of that phi j may be much smaller than the dimensionality of the x itself. And these phi j f x are called basis functions. And so this says the problem is similar to what it was earlier, except it's w naught plus wj to phi j f x, where phi j f x are called the basis functions. So we now need m weights for basis functions instead of d weights for the features. So we are somehow replacing the problem. And with a dummy basis function phi naught of x equal to 1 corresponding to the bias parameter w naught. So we can write this as y of x comma w is 0 to m minus 1 wj phi j f x, where w is this vector of all these weights. So now we are no longer looking for number of weights equal to number of input features. We are saying number of weights is equal to number of basis functions. So this is how we transform the problem linear regression with m basis function. We use m because it's like it's the model we're using. So what are these basis functions? There are many possible choices for basis functions. Choosing a polynomials of x is good only if there's one input variable. It doesn't work well with more complex situations. Gaussian basis function is a good approach where we replace every one of those phi j's with Gaussians with different means and possibly variances also. They could be sigmoids centered on points, or they could be Fourier basis functions, wavelets. There's all kinds of basis functions. Gaussian is probably the most commonly used one. In this case, polynomial basis of one variable, we saw that already. Phi j of x is equal to x to the power of j, and difficult to formulate when x is multidimensional. What do you mean by a power of j when x is so on? And this graph is showing what the different powers of x are. So I would use different powers of x as the basis functions, and we are trying to find out the weights for each power of x. And for x versus x to the power of j, where j we go from 1, j equal to 1 means this green line, j equal to 2, j equal to 3, j equal to 4, like that, you get all these. So with polynomial basis, you can have that. But once again, I'm saying it's good for when x is a scalar value. Can we use polynomial with d variables? And not practical to use polynomial basis functions. I tried to do that on this slide. And you can see phi j of x is defined as x to the j. It means it's of this particular form. And then y of xw becomes pretty complicated here with several weights for the x's and the cross values x1, x2, and so on. It gets a bit messy for polynomial. Uh, Polynomials are global basis functions. Local basis functions are more appropriate. And so this is the most common version. Maybe Mihir is going to be covering this polynomial Gaussian basis functions. Is that right, Mihir?
Yes, Professor.
Okay, all right. This is the example he's going to do. He's going to talk to you about regression with basis functions, maybe the coding part of it. But let me introduce the background for it. It is a Gaussian basis function looks like this. The phi j of x is exponential of x minus mu j over 2 sigma squared. This comes from the probability, Gaussian probability distribution. The bell-shaped curve, which is shown over here, the bell-shaped curve is defined by this, where mu is the mean and sigma is the standard deviation. Sigma squared is the variance, and that's how much the bell-shaped curve stretches. And mu is the center, the mean of that. And so the basis functions would have different means. This shows phi j of x as mu j, which means a whole series of basis functions like that. Does not necessarily have a probabilistic interpretation. Usual normalization term is unimportant since the basis function is multiplied by wj. Mu j govern the locations of the basis functions can be an arbitrary set of points within the range of the data, or can choose some representative data points. Sigma governs the spatial scale and could be chosen from the data set, example, average variance, and several variables. So x is the input, which can be exponential. I mean, which can be a vector, not exponential, it's a vector. This is an exponential here. A Gaussian kernel would be chosen for each dimension. For each a different set of means would be needed, perhaps chosen from the data, so we can generalize it to multidimensional space as well. So they solved the same problem with the same data set using Gaussian basis functions. And okay, let's see. Gaussian basis function fit, s is equal to 0.1. So they used a small sigma, which means it's going to be fitting this data like this, pretty noisy. And here you're using s is equal to 0.5. It is the in-between value, and s is equal to 2.5. And WJs for the middle model, when they use this, the WJs look like these values, all right? So you can solve a problem of regression by using, not polynomial, but you can also solve it using basis functions. Of course, you might say, look, that the polynomial looked pretty good, but that was good for a one-dimensional case. Here again, the data is one-dimensional, but for multi-dimensions, you're better off using a Gaussian basis function. And the question comes in as, what were the means that they used here? And although it doesn't say, this graph doesn't say it, it might be over the space that shows a set of basis functions that go between 0 and 1, all right?
Professor, there's a question by one student,
Yeah.
Jonathan. So his question is, what is a kernel in this basis function linear regression problem?
What
What
is
is
a
a
kernel?
kernel? Yep.
What is the, okay, I hadn't used the word kernel, but I guess it's an appropriate use of the word here. So we can think of this as a Gaussian kernel function here. So this is a Gaussian kernel which maps any value of x and a given value of mu j into a number. The word kernel is a very important word in machine learning, K-E-R-N-E-L. What is a kernel function? Kernel function is k of x, x prime. If I give you 2 points, k maps x and x prime to a given value. What does that mean? If x and x prime are vectors, kx prime is typically how similar x and x prime are. If the kx and x prime are exactly the same, then the kernel value, maybe it's equal to 1, one extreme value. Maybe it's going from, 0 to 1. So it could be 1, and if they're very different, it will be 0. Otherwise, it's somewhere in between, right? So like that, we have here a Gaussian kernel, which is a function of any point x in the space, and a particular mu j is a Gaussian kernel. So we can think of it as a Gaussian kernel, and I called it as a Gaussian basis function. That's all. There's different usage of the word. Okay. All right. Okay. Any other question?
No questions at this point.
Okay. All right. You're going to cover basis functions again, so I'm happy that you'll go over it one more time. This is an important topic because first of all, I wanted to convince you that regression is a useful problem. It can be used to solve things like search engines, to build better search engines, to solve insurance problems in setting a premium, to drive a car, so on. So all kinds of applications. This radial basis function also have a certain inspiration, as a biological inspiration, that we have, this is a diagram here, what called an RBF, a radial basis function network. We have an input X and a linear output here, and there are Gaussian RBF units. These are all based on different centers, different means here. And so we are running two values through this, and it is computing the values of the basis function. I guess these are the two values in the sense the input vector. This is the input vector, happens to have 2 dimensions. And that vector is being processed with all these kernels centered at different points. And that each of them is computing a value. And we're figuring out the weights Wj of all of these. And we're using a linear classifier at the output. So this is how the human eye, the nervous system contains many examples. Local receptive fields in the visual cortex. So isn't that interesting that the receptive field region distance to the center, that when we are looking at something, we are not scanning the whole region in front of us uniformly. We're focusing on points there. And there is a receptive field for that receptive region around it. And it gets weaker and weaker at the end, okay? So this is called fixation of the eye. When we are reading something, a book, let's say, you're reading something, your eye is not, you don't have a uniformly scanned image in front of you. Your eye is focusing on the line you're trying to read. And it's sharply focused on a particular word. And the receptive field gets an approximate input from points away from the field, as if it were a Gaussian. So there is a high value in the middle and it goes down and down. And so that is what is being sent to the brain. And then as we are reading, we are going from one fixation to the next fixation. And it's not continuous, it's discrete. The psychologists have studied, cognitive psychologists have studied this and said when you're reading and the eye is fixating, let's say from left to right if you're reading English, and so as we jump from word to word to word, we are getting a very high resolution input of some point in the word and then low resolution input from the sides. And we go on. And which is why they say that when you're trying to read a book fluently, you don't notice some typographical errors. But when you specifically go and look at it in detail, each word, and we are actually looking for typographical errors to proofread or something, then you'll catch them. But when you're trying to do fluent reading, you don't catch them because we are not exactly looking at every letter of the word and getting approximate versions of them, and we keep on reading as if there were no problem. I think you would have seen all kinds of puzzles on the internet. I've got quite a few of those lately, which says, here is some gobbledygook for you. A whole bunch of numbers and letters. It doesn't make sense at all when you look at it first. And then they say, look at it again and again and again. And you say, oh, okay, I can see wherever you wrote 3, that's probably E or something like that. And it becomes a more fluent reading. In a way, it's a little bit like this, how the eye is getting some approximate versions of it. Anyway, I'm digressing a bit there, but the radial basis functions are very popular because they're easy to implement, and they're also analogous to the human eye if you're trying to model the human eye for something. So how do you determine the centers for the means? One is k-means clustering. Choose k cluster centers. Mark each training point as captured by cluster to which it is closest. Move each cluster center to the mean of points it captured. So you can say, look, we have a bunch of data in a two-dimensional field here, and we say, well, can you find some finite number of cluster centers for the data? And this is showing the centers for the data. Every circle is every group of concentric circles is a center for the data, and the size of the circle is the spread of that data there. And so those are the mu and sigmas for each of these regions. So we are saying that you can capture the data by these centers here, and those become the means that go into determining the basis function means and variances. Okay, so that's one way to do that. Sigmoidal basis is a different kind of function where sigma of x minus mu j. Again, we need a bunch of mu j's, and we need some sigmas, sigmoids of that. There are other basis functions. So relationship between maximum likelihood and least squares. Okay. We show that minimizing sum of squared errors is the same as maximum likelihood solution under the Gaussian noise model. So what we're going to say here is that when you're trying to find the best set of weights, W, for regression, and you're assuming a Gaussian noise model, we saw noise in all of those cases. Let's say there is some kind of underlying function. The target t is equal to y of x comma w. So y is the underlying function, and there's also an epsilon. It's an error where epsilon is a zero mean Gaussian with precision beta. So we say that the output has a probability distribution. T has a probability distribution whose parameters are x, w, and b. And specifically, it's a normal distribution of t whose mean is y of x comma w, whose variance is beta to the minus 1. In machine learning, we sometimes use the word precision instead of variance. So 1 over variance is the precision. So when variance of the data is large, we say its precision is small. When the variance is small, we say its precision is high. Right? So it's a sensible term. Precision is how precise it is. So supposing we have a data set now, input x equal to x1 through xn, target t is equal to t1 through tn. And the target variables tn are scalars forming a vector of size n. Okay, so these are all scalars. So the likelihood of the target data that you observed, the probability of observing the data assuming they're independent. So assuming all this data is independent. So we are going to be assuming a normal distribution of the target. The noise is normal, which is a reasonable assumption. Look at this data set on the right here. It's a normal distribution. This red curve is the mean, that's the y function. And what you're observing is not exactly the red curve, but points around the mean. And it's being illustrated by this Gaussian that's being drawn centered at the mean here, shown vertically here. And so we are assuming that that such a model exists, in which case the output Y is being modeled by this W transpose phi of X, or we say that this probability of this target vector T is given by the product of all of normal distributions here, where mean is W transpose X, phi of X, and then beta is the width of this particular variance here. Okay, that defines it. So once we have a likelihood function, which is a product of normal distributions, the log likelihood, we take the logarithm, this product becomes a summation now. And in a particular case, using standard univariate Gaussian, this is a one-dimensional case, then so we usually use log likelihood instead of likelihood. Okay, why do we use log likelihood? Is when you take the logarithm of this likelihood, this product becomes a summation, and we take when we take a logarithm of a normal distribution is usually written as exponential, right? So when we take log of an exponential, those two cancel out, and you get a very simple expression, and which is what is being shown over here. So using univariate, this expression has this particular form, and where ED is this expression, because there's a squared expression that occurs in the normal distribution, where you have x minus mu squared, which is what is showing up here. So this is some algebra that goes on here to show this part. So you see, regression has some interesting formulation. Okay. Okay, determining maximum likelihood. The likelihood function has this form. We'll show that the maximum likelihood solution has a closed form. So if likelihood has this form, where ED, so there's a term ED, ED is this one, sum of squared errors. Sum of squared errors plus all these terms. We'll show that the maximum likelihood solution is a closed form. Take derivative of this logarithm and set equal to 0 and solve for W. Since these are all independent of W, these terms, we only need to take the derivative of the second, this term here, ED of W, or take the derivative of that. And so solving for W, we obtain WML is equal to phi plus T. So the closed form solution is a very simple formulation. It says the weight vector you're looking for consists of a matrix phi. This plus is a particular inverse, and it's called as a Moore-Penrose pseudo-inverse, which is defined as phi plus is phi transpose phi inverse phi t. All right. What is this phi? Is a design matrix. Design matrix is a simple thing. Consists of n samples or the n rows, and the columns corresponding to the m basis functions. So these are the m basis functions, and so that is this is the form of the design matrix, and we'll have to use the Moore-Penrose inverse of that multiplied by the target vector target values. That gives you the solution that you're looking for. So in a way, this whole linear regression problem becomes very straightforward from a programming point of view. You just need to arrange a design matrix of your data set where you're replacing the features with the basis functions. Okay, so that's how you need to arrange your design matrix. And you have got the target values, so you just do the Moore-Penrose inverse and you get the answer. Design matrix again is M basis functions represented as n-dimensional vectors. Okay, W naught plays a role here, and it's replaced by feature value 1. This is at a specialized case of what you're dealing with, a bias term. And this gives you some explanation of that. And these slides here are about maximum likelihood for precision beta. You can also compute. What about the variance? What do you assume for the beta? And you can come up with a maximum likelihood solution for that also. There's some geometrical explanation of it. Then we say difficulty of direct solution. The closed form solution leads to numerical difficulties, not uncommon with real data sets. Of course, when you're trying to design a search engine solution where we have hundreds or maybe thousands of features that are used to figure out what web page is good for you, a closed form solution may not be the right approach to it, because numerical problems can be addressed using SVD, singular value decomposition, so on. So those are some of the things that are indicated in my linear algebra slides, which we didn't go over, but SVD is over there, which is why we use the method of gradient descent. And criterion FFX is minimized by moving from current solution in direction of negative of gradient, steepest descent. So you have a new value for the weights by taking the old value and taking the derivative of the loss function. And we just saw what the loss function looked like in the previous slides. So that's what we do with gradient descent. This graph kind of motivates why we're doing this negative. If you're standing on this side, here we are plotting f of x equal to x squared. F of x equal to 1 over x squared. Okay, so this is 1/2 of x squared. Okay, that's what this is, 1/2 of x squared. So if you assume a value solution here, then you are trying to find the minimum of this function, 1/2 of x squared. The minimum occurs when x equal to 0. So if you thought that the answer is somewhere here, you have to head in this direction, decrease the value. If you're on this side, you have to increase the value, right? So the derivative is going to be positive or negative, and you multiply it by this negative quantity, and that will give you the appropriate direction for that, all right? For x less than 0, we have f prime of x less than 0. For x greater than 0, we have f prime of x greater than 0. So that's where the sign comes in. Eta is just a step to see how much you're going to move. So this is this particular equation is called gradient descent. Gradient descent. Eta is the learning rate, a positive scalar. Okay, this explains gradient descent with multiple inputs. That was the one-dimensional case in the previous slide. And here we're talking about derivatives in multidimensional space. Stochastic gradient descent is the same thing, but we do it over batches of samples rather than all the samples together. This is n samples together, and we start doing this over smaller number. And there are some slides here about how do you choose the learning rate, and are there any ways of heuristics for determining the learning rate. And constant learning rate is default in Keras. Keras is a version of a library function for Python, version of TensorFlow, I think. And so there are all kinds of sequential methods that do this. Okay. All right, there are computational issues. Okay, I'm going to stop here and have Mihir take over and cover again these basis functions from a programmer's point of view.
Sir, can you make me the host so that I can
Yeah,
join
I'm going to
multiple?
do that. Mhm. Mihir, while I was trying to do that, I got preempted. Just hold on
Okay.
while I make you the host. Okay.
Okay.
Hold
So
on.
I can start.
Hold on just a bit.
Okay.
And okay, I made you the host. Change host. And I need to click on that. Okay, done. Okay, so you can take over now
Okay.
and go over it, maybe in crystal clear terms, programmer's point of view, what I just went over. Okay.
Yeah.
All
Sure,
right.
Professor. Okay. So hello everyone. I have shared the link to the Google document, the Python notebooks, in the chat section. I have also posted it on Piazza, and it's also available on UB Learns. Let us know if you have problems connecting to the Python notebooks. And this time, I think you'll be able to edit the Python notebooks on the web instead of downloading it and running it locally. If you have problems running it on the web, you can always download on your own computer and edit the Python notebook. It is recommended that only one person from the team edit the file and share the screen while doing so, and rest of all the team members should discuss and come up with the solution. uh, I'll just start sharing my screen and go over the problem statement. Again, we are working on the same data set as we worked on in the previous class. The only difference is last time we implemented a linear regression solution with closed form. Right now we are working with Gaussian radial basis functions based on top of linear regression model. And the solution that we are building is the closed form solution again. So what changed since last time? The genesis equation will change. So currently last time we had the genesis equation of the form y equals x times w. So it's basically the function of the original features x and w. But in basis functions, what the change that has to be made is, instead of taking the original feature x, we have transformed that by using j basis function, and hence we have phi of x. Now, phi of x, the dimensionality of phi of x will depend on how many basis functions you have. So if you have, let's say, 3 basis functions, then the dimensionality of phi of x would be n times 3. And for designing the matrix, you'll have to use the Gaussian radial basis function equation, which takes the form as shown here. You have to have x, which is your original input data set. X has to, and then you subtract that with mu, which is the mean of your data set, and then which has to be multiplied with a diagonal covariance matrix. You have to invert the covariance matrix and has to be multiplied again with x minus mu. So in order to implement this, you need mu and covariance matrix, which has already been implemented and given to you. So it's pretty simple to come up with the design matrix. You just have to use this formula. And the resultant design matrix would look something like this. You have m basis functions and you have n data points. So x will be transformed to this design matrix phi with n cross m dimensions. And that's it. Just go through the steps. Step 1 to step 5 have already been implemented and given to you. Step 6 to step 9 are to be implemented by you. And that's all. If you have any questions, directly email to us and we'll be available in each breakout room shortly. So let's start by creating the breakout rooms first. So we have 52 participants and we break you down into 5 rooms. Okay. Okay.
Hey guys.
Hi.
What's up, Maya?
Yeah. Hi, Gaurav.
So which is we have breakout room 3, right?
Yep.
So our team is Gan and
Everything okay here?
I guess we all were studying the problem.
Okay. Who is leading this breakout session? Who is sharing their screen and editing the code? Gaurav, you are leading this group.
I guess I did it last time, so if Mayank or
Okay.
Vineet or
Mayank,
anybody wants to
Vineet,
take over.
Sholing, Michael, anyone?
Uh, um, I'll lead it.
Okay.
I can share.
Okay. Thanks,
Um,
Michael.
okay. All right. I'm sharing it in 1 second. All right. I'm gonna start by adding everyone's names.
Last time we just put our names in chat, so it's easier for you to copy paste. So
Okay.
I'm gonna start with doing that. Yep.
All right. I'll open up the chat. It looks like we have 9 people. Is that everyone then?
Yeah, except
Okay.
the professor. I think we should.
Okay.
No, we do not, right? 1, 2,
I think we have
6,
10
7,
with
8,
him.
9. 9. Yep.
Yeah, so
Yeah.
that would bring us at 9. Okay.
So first step is creating a design matrix using scaled features and mean and spread. So design matrix, does that mean that's the basis underscore
All right.
variance? Yeah, Michael?
By the way, if anyone comes up with ideas for the code, please put it in the chat and I'll start implementing it. I'm not really a seasoned programmer, so yeah.
So is the basis underscore variance the design matrix or the features? Any idea? Scale features. So we are basically finding out the W, right?
Yeah.
Yeah. So mu j must be the center of the jth radial basis function. Some kind of instruction. Yeah, but what's the basis function in this case? Do you have any idea, Goodleen? Is the basis variance the basis? Yeah, okay. So basis variance is the basis function, right?
So phi of x is basically exponential of that minus half into x minus mu times transpose. Like you have that function in PPT. You can just take that.
But don't you think so? Basis variance is the basis function, like he already gave us that. Because you see, on basis variance equal to np dot zero number of basis function, number of number underscore of underscore basis function. Yeah, we need to implement that. I'm confused as to what is mu j. It's the mean, but like, do you guys have any idea where do we get that mean from? Has he already created that somewhere, or
They have calculated it in step 5.
uh, is that the basis underscore means,
Yep,
Mayank?
looks like that. Basis underscore means is so the mu j, and then the variance would be, I think, the summation part.
Could you repeat that? We couldn't hear you. Your volume was real low. Step 5 was.
Okay, so the basis means is supposed to give us mu j. So I think they are equivalent, and then the variance is supposed to be the like the summation of j part.
Okay. The whole basis variance is the summation of the j part, like the.
So yeah, so they have given like spread that is a summation of j. So that is already implemented. So I guess it is supposed to be the entire, like the complete thing.
Hmm. Okay, so Gurleen, do you think so? Basically, basis underscore variances is the spread, right?
Yeah.
Okay. So basically, they have given us two things, and we need to find the whatever the sigma jx. Is it sigma or is it rho?
Phi.
Psi. Okay. Phi rho phi x. So just like take the exponential minus 1 x minus. So what's x though? X is the scaled version of the. Is it the x train array? You guys think that is the x? I could start coding, Michael, if you want, because we have
Okay.
less
X,
time
Um,
left. It's like 6:38.
X is the entire example.
all
That's what
right.
I'm assuming.
So it's the x train array, right?
X train array. Yeah, but in the design matrix above, that's what was confusing me. It says phi 0 x1, right? So phi 0 is our first graded basis function, and x1 is the entire first example.
I don't
For
think
example, if
so
you
though. Like, do we need to worry about the repeated application, or we just have to make the design matrix at first, right?
yeah, exactly. So do you know how to?
Yeah, I think I'll take over. That's okay.
Sure.
Okay. I can stop sharing and you
Yep.
can. All right.
Can you guys see my screen?
Yep, I can see it.
Okay, I'll. Michael, can you send the whole everyone's names so that I'll just copy paste here and I'll start coding first.
Okay.
So I'm not sure about how to do the exponential. So if anybody can look that up, that'd be great. I'll just do the inside part.
You can just use np.exp for the exponential.
Okay, np.exp. So should I just call it design underscore matrix equal to p.exp? What are we like raising it to, like exponential or like, okay, it grows it's on its own? Is it like that, Vinny?
You are raising it to a value, right? P raised to the power something. That's
Yeah,
in the
so
formula above.
that value is gonna be.
It's going to be dynamically calculated. Can you go above?
Okay, so we don't need to worry about that, right?
Yep.
I just wanted to know that. Why don't I have access to that? It should pop up itself, right? This one, xtrain underscore ARR. I'll go ahead and check that out later.
If you just run it one time, I guess it will be, since it has not been run. It's not showing you in the
Got you.
RAM.
Oh, the barcode. Okay, I got you.
Yeah, you can just run this cell and create another cell and do the rest of the part there.
I do need to take transpose of these, right? Is it np.transpose?
Just a dot T works.
Got you. And this is the is this the spread? So should I just like write multiply? That's it.
Not multiply. What we're supposed to divide it by the spread.
We're
I'm
supposed
just
to
looking at
divide
the
it?
formula. I'm just
No.
looking at the formula. Give me a sec.
Okay.
The thing is that this phi x value is going to be one value, right? But the array x is not one value.
Okay.
So for instance, it's computing for n cross n for n examples and whatever number of features we have, 11 or 12. So it's a square matrix we have. And it's going to output, it should output a column vector, but we won't get that until we apply some sort of summation over there. So what you have done right now would not work. That's the missing link here. Maybe let me just check professor's notes one second.
I was thinking first we could make the design matrix, and so yeah, you're right. The cause design matrix only will be for X train array. We will have to make it.
Even for X train array, like the construction of design matrix. Okay,
Hmm.
so how many rows are going to be there and how many columns? So we know the number of columns. That's going to be equal to the number of radial basis function we have. So that is 3. So we
Yeah.
know the columns are going to be 3. What are the number of rows? So the number of rows are going to be column. The total sample size. For instance, we have n samples. So that's what the number of rows are going to be. Now, how do you put 11 features into one radial basis function? For instance, computing 0, comma 0. That is the first example and the first basis function. So you need to put all the attributes or all the features, for instance,
Yeah.
11 features, into one basis function, compute one value, and store that into first row, first column. So that's what we need to figure out how to sum that up. Once we
And
have
then we
that,
need to do that for whatever number of xn.
yeah, exactly. That's what we need to figure out. That's the only missing link here. I'm logging it in, logging into Ubelons. It just logged me out. So it's taking me for the
So we can't use the pseudo inverse. What's with the pseudo inverse thing?
that's
Train
going to
using.
come later after we're done with this design matrix.
So for maybe for design matrix, we don't need to use X train array. We need to make the design matrix based on the features.
X-train array are the features.
X train array are the features, or is it the sample set?
What do you understand by features?
Features as in like the training data, right?
The training data, yeah. The training data and the test data. Both will have features. It's just that the data is split across them.
Because in the steps instruction it says later on that train using the linear regression algorithm. So that time we should be using the training data set, right?
No, we'll be converting the training and testing data set together. We'll be finding W based on training data, and then we'll be finding the accuracy on the test data, which has been converted by the radial basis function to figure out how our model is generalizing on the test data, if that
Gotcha.
makes sense.
Have you reached somewhere? So if you want, you can take over. I don't mind.
My system is hanging, that's why I'm not taking over.
Gotcha.
Also good. If anybody else has an idea how to sum that up into a real basis function, please go ahead.
Should I try Googling? I don't know.
I guess the best thing would be to look at professor's slides.
So we will have to make two loops, right, to make the matrix.
I don't
W.
think we need loops since we have numpy arrays.
Yeah.
We can just vectorize and that'll be faster.
Or else, Vinit, can we write one for loop?
No, we should not. We can just vectorize. That will be faster. We're using GPUs, right? That's the only
Mhm.
reason we're using GPUs. NumPys will work faster. So we can just multiply them together using NP dot and sum them up using NP sum if wherever summation is required. That will be much faster than a loop. We can also write a loop, but that will be slower.
If you need help with it, you can call over me here. Like,
Yeah, I guess we should like just understand how we're computing phi. Yeah, can somebody ping him on
just ask for help.
the chat itself?
Uh, yeah, he must be. Just ask for. Oh, he's in some other breakout room right now, I guess. Okay, I have invited him. I found some code. You need. You wanna see that?
I'm trying to not look at the code, but just look at concepts so we can actually come up with a code ourselves.
So we know the number of centroids, right?
Yeah, it's already been computed. The number are 3.
What are the centroids? Is that the number of basis function? No, right?
Yeah, those are the number of basis functions. So it's the
So
center from which the
this guy is saying
the
that we
mean
just.
and
Oh, this one guy is just saying that we loop over the number of centroids. Uh, get the ith centroid. So ith centroid would be like So we need like centroid is basically like a random row from the training data set, right? Like from the features, right?
I guess centroids are computed based on k-means. You see many batch k-means
Yeah,
imported?
yeah,
That's
yeah.
right. So the way
So,
k-means works is it actually selects centers based on Euclidean distance from all the points.
okay, so we need to do model dot centroids. Okay, so
No,
we that's
it's already done. That's done.
that's the basis underscore means.
Yeah.
That's the
So if
basis
you
underscore.
print, yeah, so if you actually print basis underscore means and basis underscore variance, right? You'll have three centroids and three means and three variances computed for all of them.
Oh, okay. So if I just say basis underscore. Okay, so that's the array of basis underscore means. This one, right? So we have the
Read
centroids.
the
We
first one. Yeah.
so
So it's just a matter of multiplying the centroids with all the data points and how to sum them up. So the formula is not clear to me. The one. Once he comes, like we can just ask him.
what to so if like I'm looking at this one guy's answer, like not answer as in like the code, and what he has done is he has done NP exponential minus distance of the whatever the centroid array centroid number is, and divided by sigma. So he has done division. So I don't know
Yeah,
why we are not doing
that
division.
that's for one variable, and that's
Okay,
in the notes as well. That's for one variable.
okay, that's for
So
one
for
variable,
one feature.
one feature.
Yeah.
Okay,
So how would we do it for two features? Or basically 11 features or two features. Um, are we supposed to take the mean of it or what? Let's just start with the mean of it.
I guess we are supposed to use the mean because
Yeah, I guess we'll just take the mean then. Okay, so let's start coding. Okay, so let's take X train array and subtract the mean from it.
like the basis underscore mean.
Yeah.
S-
So once
okay,
we've done that, we'll
then
take the sum across the column.
so the sum across the columns is already given to us as basis underscore variance. Yep,
Uh,
and so that was my initial question. Like the transpose of these two, like the difference between these two and the transpose. Do we multiply it by the sigma or no?
we don't have the sigma, we have the variance.
We have the basis underscore variance. That's not the sigma.
Yeah, since you're saying it's adding up the distances.
Yeah, because over here it says for labeling,
Hmm.
so it's going to all of them, and it's also taking square and stuff, which this guy over here is doing.
Yeah.
Okay. So what do you think? So we did
Can you
subtract.
print distances once?
Oh, you want me to print what?
Distances, the array distances, the shape and some sample value.
So this one, right?
Yeah. No, distances. There is an array distance.
You said distances or variances?
Distances.
Oh, distances.
The shape and first few columns. Print distances dot shape.
Distances dot.
Shape.
Shape.
Can you spell that? SH shape.
APE.
Okay.
Okay. And how many samples do you have? Can you do the same for X-ray?
It's 413. No, 517.
No, for X-train,
Oh,
the training data, not the entire data.
yep.
Okay, so it's already computed the distance
Yeah.
of a particular data point from all the center. So I don't think we need to do that. It's already done that for us. I need to take this and multiply it with the I'm in a loop here. You guys can try something. I'm just trying something on my loop looking. So
Gotcha.
you guys can try some other push.
I have invited Mihir, but he isn't responding. So, is distances the X array? Vineet, do you know? It's confusing. Create design scale features.
Sorry guys, I was with room 1 and they had lots of questions, and I guess you guys also have lots of questions for me.
Yeah.
So yep.
So
Yep.
Yeah, I'm here. So the first question is that we see like the design matrix is n cross number of basis function columns. So n is the number of examples, right?
Yes.
Yeah. So when I say phi 0 x1, so that's converting x1 all the values and putting that into the basis function. So for example, 11 features and putting that into the basis function and getting one value for that.
The first basis function. Yes.
Yeah. So that understanding is correct. Okay. So
So
how do we compute that for first value itself? How do we sum up across all the features for one basis function? Like we see the formula above, it's x minus mu j
okay.
multiplied by sigma something.
Mhm.
So so in the distances, I see there is a value like it's n cross 3.
Mhm.
So do we assume that's for the first centroid, the first
Mhm.
column is the distance from that centroid?
Yes.
So that's x minus mu I for
Yes.
that.
Yes.
Okay, so all I need to do is multiply that by the what you call as basis or the variance, diagonal variance.
The diagonal covariance matrix. Yes.
Yeah,
and that's the
so
basis
all we need,
underscore variances, right?
Uh,
yeah,
yes. So that's the. But you also have to invert that and multiply. Okay. And if you're multiplying it, make sure that everything is in matrix format. So multiplied accordingly. Okay.
okay. Why do we
So
need to invert that?
Oh, because if you look at the Gaussian basis function equation, it is x minus mu the whole square upon 2 sigma. So the variance is in the denominator, and if you work with the matrices, you have to invert it in order to get it into to the denominator. Make sense?
Oh, so be either divided by each or we just multiply it in that format.
no,
Okay.
just 1 by the whole thing, right?
Um, so right now,
So
basis underscore variance is a matrix which has elements in its diagonal. So if you print it, you'll be seeing it's a matrix. So make sure that if you're multiplying um, in a scalar format, you'll be using the values and taking it into the denominator instead of
yeah,
inverting it. So
okay, got it.
so it's a
Okay, yeah.
So the
matrix, right?
above,
So yeah.
yeah. So also like, can you explain the notation, the way the above formula is written? Can you scroll up once, one time? Gaurav,
Yeah.
can you scroll up one time to the formula?
Okay.
Uh, give yeah, so it says summation j to minus I. What does this mean? Like, I was not able to understand this notation.
Sorry, could you repeat your question?
Yeah, the notation summation j to minus I. Like,
So
what
that's
does
not
this mean?
summation. Again, that's the covariance matrix. It's a notation for a covariance matrix which is diagonal. A
So
diagonal covariance matrix. Make sense? And you have to
Okay,
invert it. Then that's why you have -1, or inversion
the
basically.
inverse formula. Okay.
Yeah, inverse of matrix
So
basically.
do we need to inverse every element inside the matrix or
yeah,
No,
just
you
yeah,
have to use basically np dot linear
inverse?
algebra dot inverse.
Ling
Yes.
Lang inverse, right?
Yep. Yep.
And other question was x minus mu j.
that's
Uh,
just the distances.
yeah. So that's the distances.
Yeah,
Yes.
yeah.
Okay. So
So we can directly just multiply that.
that's already done basically, right?
Yeah,
So we don't need to take transpose of that.
So yeah, I have given you just the mean and the spread, which is the covariance matrix. You have to basically transform your original input data set, which is uh,
into design.
38 features or how many ever features, to 3 dimensions. Okay, using the mean and the covariance matrix.
To three
Gotcha.
Make
dimension?
sense?
Like, how? No, no, no. Okay, can you repeat that statement?
So I have asked you that the number of basis function, if you see carefully, it's 3
Yeah,
in step 5. So you have to
3, 10,
convert your original input data set. How many features do you have?
10,
11.
11.
Like
11
whatever.
features, right?
Okay.
So let's say you have x1 to x10. You have 10 features. You're converting those 10 features to three features. Make sense? By using 3 basis functions.
Hmm.
Mm-hmm.
So for doing that, you'll be using this equation, which is np dot exp x minus mu. So you have 3 mu's, right? 3 mu's and 3 sigma values. So use appropriately.
Okay, no,
So those
there's
three
a
mu's
confusion.
are these ones, the basis underscore means.
Yes, it
And
contains. Yep.
and
And three.
basis underscore variances is the three sigma values
Yep.
diagonally, and x underscore train array is our x basically.
Original X. Yes, that's correct, Gaurav. Yep.
So isn't distances X train array minus basis means already?
Sorry.
Like, so what is distances exactly? Like, distance
Distances mean.
is like you have a variable distances, right? Model of a
Uh,
transform X
Right
train.
here, right
Oh,
up
so
here.
you don't have to look at that. Distances is basically used for. Yes, you're correct, Minit. You could use that, but that is just for me to calculate the to come up with
Distance
the
from the
means, to come
distance
up
from
with
the
the
okay.
variances in the first place.
Okay.
So instead of using that, you use the extrain air and basis means. Okay, that's a
So
nice
okay, so I
catch,
use
but yeah.
okay, so I use X train array. I subtract the means from all the columns, right?
Yes.
And then I multiply it with the basis
Appropriate
variance and include this.
variances, but invert it and multiply it with the appropriate variances, and then multiply again with x minus b. Okay.
Okay, so that will give me one column vector for the first basis function,
Yes, that's for first basis. In the
and
second.
then we have to do it for 3. Okay.
Yep.
Okay, got it. Okay, thank
Okay.
you.
Yep. And what about the others?
No idea.
apart from Vinith, everyone is sleeping. Mayank.
No, we are following. We are following.
Okay, just ask Vinith any questions if you don't understand, because his understanding is pretty solid. Michael, if you have any questions, just ask him. Okay.
I don't know if anybody is in the room.
Everybody
Sorry,
is in
I missed it.
It's okay. Like if anybody has any questions, like just stop whenever you want.
Okay.
So
Yep.
this must be like the column 1. I just write column 1 or
Now
whatever.
that part we can put it into a loop.
Yeah. So this one is 410 by 413 by 10, and this one is 3 by 10. So we just need to take the first column of this basis underscore means, right?
Yeah. So let's start with a loop. Let's start a for loop.
Let's start with the for loop. What should the range be?
For I comma mean.
For I comma mean. You
And
wanna paste it in.
enumerate.
Could you repeat that?
ENUMERATE.
Oh, enumerate. Okay.
Yep. In means basis means.
Could you repeat that? Sorry, I cannot hear.
Basis, the basis means. I guess we should
Basis
zip it
underscore.
and just zip it and use. We'll have to use the covariance as well, right? Basis variance. Can you print the shape of basis variance one more time?
You want to see what? The basis underscore variances?
Basis underscore variance. Yeah.
Basis underscore variances is this. It's a 3 by 3 matrix with only the diagonal values.
Okay. So are we going to use this for all of them? Can you scroll up one time?
Sure.
A little more. Yeah. Okay. This is how it would be.
So we have 410 and 10 features.
Basis underscore variance is label distance I label start 2.
So he wants us to invert this first, right?
Yeah, that will be inverted. I'm just trying to think that are we going to use the entire matrix for all 3 computations?
Yeah, I
Or
think
just
so.
going to use the first column itself?
First column. That.
Yes. So that particular column should be used.
Yeah. So first column for the basis underscore variances and first column for basis underscore means, right?
That's what I'm thinking. Just trying to confirm. Just okay. So let's just do for I in range 0, 3. We don't need to add enumeration here.
Got it. I in range 0 to
Yep.
0 to 3.
Just 3. Just range 3. You can
Or
just
should
write
I?
range 3. Yep.
Okay, I was just gonna do this, like number of basis functions.
Yeah, you'll have to write range though. Yep. And that's not.
And,
remove mean from the above line.
design matrix and PXP basis underscore means. And how do you get the column dot column or
No, bracket, square bracket.
Yep.
Yep.
Comma
Yep.
and
And I. No
so
colon required.
sorry,
No colon required.
no colon.
Yeah.
Oh, okay, no colon. Okay, so we get the 0 like whatever we multi blah blah blah, and then again the same thing, same column.
And also before taking the basis variance, right? Let's just compute the inverse of it in another variable above step 6,
Sure,
or just like
that will
no,
be
not
like
outside the for loop. Outside the for loop.
outside the for loop. Okay,
Yep.
so it will have access throughout. Okay, got you. Np dot Langley. What was that? I'll copy paste.
Ling ing and okay.
That's gonna be basis the whole thing basis underscore variance, right?
Yep. And print the shape as well.
Sorry.
And print the shape as well. Just want to see what shape comes up.
Oh, you want to
Should be
see
the
the
same.
shape? 3,3.
Not this one. The inverse that we get should be the same, but stuff. Okay, fine.
Oh.
Never mind. Okay, so we have the inverse. We have this. We have the basis mean, and the same thing for basis.
Inverse multiplied by inverse, right?
Yeah, and not multiplied. It will be np dot.
Oh, it's a dot product?
Hold on.
Because it doesn't say anything. That's why I was like,
I'm not sure about that.
yeah. That was what was more confusing than this stuff. But I think it's multiplied. We can go with multiplication for now and then circle back. What do you think?
Okay.
So this goes inside the loop. Then we get design matrix, like basically the first column, right? So should I just do this? And
Yeah, you'll have to declare it first. Or will it just work? I'm not sure. Let's just try it. If it throws an error, we'll see.
sorry, I'll just do this design matrix
Yeah.
column. So it will go for that column. And do you want me to print this one out?
Yeah.
And just increase the I in for loop. Which I increase?
No, not required.
Not required. Okay.
But it will throw an
Invalid
error.
syntax.
Yeah. So declare a design matrix.
Matrix. Should I use np.00?
np dot array or 0, like whatever. Like you can just see the
p
syntax
dot
from above.
array.
And if you can just pass a function. Okay, scroll up for the 0 part.
Okay, it's not. Oh, which one?
Scroll up a little.
This one?
Yep, just do np dot zeros and number of samples, comma 3.
So that's going to be 4, 1, 3.
You can just do x train shape 0.
X underscore train underscore dot shape.
0.
Where?
After shape here, square bracket 0.
Square bracket 0. Okay. No.
And
Just saying
np dot, is the spelling for 0 correct? No. zeros.
I could use a hard like 4, 1. What was it? 4, 1, 3.
np dot zeros.
ZE. What do you say? It's ZEROS. Oh. Still invalid.
It's showing right design underscore matrix. That syntax is invalid. Left side. No, in
Yep.
brackets, comma I. That syntax.
Yep. How do we
Write colon before comma. Before comma.
before? Still invalid.
Yep. No. It's not the one. The error moved.
I should remove this.
No. The colon is fine. The error
Yeah.
moved to basis means. Look at the pointer in the error.
Oh, over here. So I should. Do you want me to do one more colon here?
Yeah, and then inverse.
Data type not understood.
Look up documentation for inferior.
In the design matrix, we are supposed to multiply it again by x train array minus basis means.
So the shape is
So-
supposed to be in a tuple. NP zeros,
Yeah.
but another parenthesis in and out. Gurleen was saying something else. Sorry, I interrupted.
Yeah, it's okay.
Just put two parentheses before 413 and after 3.
Two parentheses you said?
Yep.
One here and one here.
No. After 3.
After 3.
Yep.
Sure.
And you can just print the shape of it after that. What is the error now?
Start shape.
What is the error?
Still 413 comma
Okay.
3.
Yep. Okay. The error is
And
so
the
this
error
one.
is that it is operands could not be broadcast together with shapes.
Okay, so it's a different error. That's fine. Earlier it said it could not understand the data type.
Yeah. So this one is probably related to this 413 comma 10, and this one is 3 comma 10.
No, it's just 3. Why is it giving us
Just
3?
I don't get it why it's 3. Oh,
So when you're multiplying it, that's why it's saying that. So remove the multiplication part for a second.
it's 3 comma 3.
Yeah, but you're fetching the first column, right?
So should I remove this?
For 1 second, remove that. Just trying to see what the error is. No, not just the multiplication. The inverse INV
The whole
colon
thing.
icon. Yeah. One more.
See, it's not related to the multiplication. I don't think
Yeah, good. So let's.
so. So it's probably related to these both. So
Yeah,
because
it's related to basis underscore means that
I
bracket thing. Yeah.
yeah
Yeah, print the values of basis underscore means.
means 1, 2,
Uh,
3, 4.
Print the shape.
It's 10 by 3. 3 by 10. Sorry. So we should inverse it, right? Like 10 by 3. Take the transpose or no?
No, so we should be taking the first row, not the first column.
We should be taking the first row because
Yep.
we have 10 values here and we need 10 values there. That's why.
Yep. So we have 10 columns in both, right?
Yeah. So I'll just reverse these
Revert
both.
that. Yeah.
But won't it just go over for 2 rows?
No,
3
it will
rows?
broadcast.
Yeah,
It will
that's
broadcast.
fine. That's fine. That's fine. Then. Okay, so what? What just happened?
Fine. The multiplication error. So you added, you
It's
subtracted that, then you took the transpose, so it became 10, comma 413. That's fine. That's fine.
that's fine.
Yeah, that was correct.
That was correct.
Yeah, the earlier step.
Okay.
Okay. So what happened is the basis means, right? It's a 3 comma 10 vector, a 3 comma 10 matrix, right? You took the first row and subtracted it from x train. So it broadcasted and subtracted it entirely. So what you would get is 413, comma 10.
Yeah.
Then you took the transpose dot t, and then you're trying to multiply it with 3 comma
3
something.
comma
And that,
whatever.
yeah,
Only 3.
that's the error that you're getting while you're multiplying. So x train minus basis means is fine. Up till here we're fine.
So
Yeah,
basically,
so for the second part, we are supposed to multiply it again by x underscore train array minus basis means. So he said we are supposed to again do the x minus mu thing after the inverse.
got you. So that we
After the
have.
inverse.
So
Yeah, so
basically,
if you see, if you see the formula, it is the spread, inverse of spread. But after that, you have another like parameter, x minus mu again.
Yeah, but that's the covariance matrix. So that's just a notation. That's what I asked him later on.
Yeah, but
So that's the variance matrix which he computed in the basis variance. So we just
yeah,
need to take the inverse of that.
he said that we have to multiply it again.
Yeah, multiply it with the inverse of the basis matrix. That's my understanding.
we need. I'm giving you the remote control if you want to go ahead.
Mhm. Okay. So the inverse, I just want to see the shape of it first. It won't be. Repeat that. Okay. Can you scroll back? Like
Yep.
it's just moving a lot for me.
Sure.
Okay. So we have a 3 comma 10, and we don't need the transpose then. So now we have 413 cross 3. So we need to multiply it with that. We need one column vector, right?
Yeah.
So are we supposed to multiply it with just one value?
No. So I think Gurlin is right that we need to have the same shit over on the right side of the multiplication so that we have equal shape matrices.
Yeah, maybe we need to just broadcast.
Because
This will work,
inverse.
but if its formula is correct or not. What does it say?
Oh,
Can
you
you
want
see
me to
the array?
scroll? Yeah. It's could not broadcast input array 413, comma 10 into shape 413.
Oh, I'm pretty.
Yeah. I think the whole thing is regarding like on the one side you have. Is it? Is it? It might be. We need to multiply basis underscore means by inverse
No, no, no.
Yeah,
because we won't get a size of. So we have 3 by 10. We have 3. So how will we get 10 if we want to multiply it by x train array of 413 by 10? 413 comma 10. Sorry,
413 comma 3
comma 10.
or
Right?
10.
Yeah, 10.
Oh, sorry, 10. Yeah, depends on the kind of multiplication we're doing. If we want a matrix multiplication, we'll use NP dot. But if we want a hammer dot product, we'll just multiply directly.
Do you want me to send you this code? Can you edit? Yeah, there you go. 'Cause I'll stop sharing when I wanted to do
Mhm.
something. Okay.
Okay, got it. What we've done is we've subtracted. Okay, so the mean, whenever we mean as a 3 cross 10 vector, right? So we have 10 points for the mean. It's x1 dot x2 dot x3 dot x4 dot x5 something. So we need to compute the distance between those two. So the distance is not just x train array minus mean. We actually need to square it, sum it, basically try to find the Euclidean distance and then take the square root. So that will be the distance. So we will get 413 comma 1 column vector. And then we need to multiply it with the variance. So who has the latest copy of the code? Can we try something? Hello?
Yeah.
Who has the latest copy of the code? Gaurav, you have, right? Can you share one second?
Yeah, sure. Just a second. So, just sure. Yep. Go ahead.
Okay. So let's not do it entirely in one step. Let's just do it part by part. Can just go to the
I'll just take this here.
Okay. I'm removing this all for now. Let's just comment it out. Okay.
Oops.
I'm not sure what's happening. Okay. Okay. So this is, we just get the corresponding coordinate subtractions: x minus x, y minus y, z minus z. And for 10, let's just square it up, since we need the Euclidean distance, I'm assuming. I'll just be printing the shape for this. Let's just print this. That's not what you should get. Can you go down one? Oh, sorry.
Yeah. Okay.
Okay. I'm not getting the shape. Why the error? Can you scroll down just a little bit?
Sure.
To the error.
To the error. Okay. Access an invalid keyboard to
Okay.
unfunc
So it has
square
to be
root.
added to some. Okay, fine. Just add it. Right. Okay. We're getting 413. That's fine. Let's try to multiply it with and like come on. Like Mm, can you scroll down to the error?
Sure.
Sorry, I'm bugging you.
No problem. I just need to submit something else. That's why I'm multitasking right now. Operands could not be broadcast together with shifts for 1, 3, and 0.
Oh, okay. Can you move the dot shape? Okay. Fine. Mm, what- what's this called? Python? Okay, cool. Sure, cool. Got the distance multiplied by that. If I try to save it, that matrix. Oh, cool. So shift, and we got the rest of the power. 1, 2, 155. Okay, can you call me here one time? I did do it, but we
Sure.
need to check how correct this is. So give him a
Ask for
control.
help. White House. I invited him. White House.
Cool.
Twice. I don't know if he is on the call. Lama.
He probably is. There's just a lot of doubts.
Okay, we need to answer my question. What is one technical mechanism to avoid brute force attack?
What?
What is one technical mechanism to avoid brute force attack?
And what kind of brute force?
Like
DDoS?
password attack. If someone's trying to guess your password,
Like
is
you
there?
should add. Yeah, you could have multiple characters, right? Increasing the number of characters.
Yeah, I just wrote
Each
use of special characters. Do you think that's right?
special characters, digits, uppercase, lowercase.
Let's go with that. Just undo version.
So if okay, in any case, we have the design matrix here, right?
Hmm.
So we can go on with the following process. If anything's wrong, we just need to change the design matrix code. Everything should flow as is. We
Yeah,
can
we
start
just
with
need to
step
get the.
following steps.
Oh, now it's easy. Now we just need to get the transpose, multiply it,
Yeah,
get the inverse, and get the transpose again and multiply it by the testing data set. Correct?
yeah. So if other people want to like try that, those who didn't get a chance last time.
Is anyone interested? To be honest, I don't know. I could open up my last time submission and copy paste some of the stuff.
We don't need to. It's pretty simple, straightforward. Let's just go up,
Got you.
do
Sure.
what we need to do. And
If
come
anybody
back.
wants to go ahead, please feel free. I'll give out the remote control to anybody. Or to accept all requests. Yep. Mayank, do you want to try? Mayank, Gurleen, Michael, Vinci. It's just getting the transpose, multiplying it inverse and multiplying again by the testing data set.
We can just start if nobody is responding. That's fine.
Go
They
ahead.
can just interrupt.
Sure. So that's gonna be called closed form solution, right?
Yep.
Or, since they have written, okay, NP dot, we are using dot product over here,
Yeah.
like, sorry, over here. These two, right? That's a dot product, right?
Yeah.
Not here. So multiply, I'll just make a variable multiplied equal to design matrix dot t np dot design matrix dot t comma design matrix, right?
Yep.
I haven't scrolled. I don't want to scroll up again. That's why. And then we just do.
The
We're
inverse
finding the
effect.
W, right? Yep, we're finding the W. So W equal to NP dot multiplied
Inverse of
right,
multiplied.
inverse of multiplied. Okay.
Yep.
So that's gonna be NP dot ling lang dot inverse, right?
Yep.
Liang
Lin alc
linalec
dot
dot
inv
inv of
multiplied.
multiplied comma, and we're
Design
gonna
matrix.
multiply that by the design matrix or
Yep.
the okay
Transpose the design matrix.
design matrix,
This wouldn't work.
and we are gonna we should again multiply it by the testing data set, right?
But this wouldn't work.
This wouldn't work.
This would throw an error.
Okay, I'll
The
just check.
W statement.
I'll just run this and see. 3,3. I don't know where that 3,3. Okay, that's from here. So it's saying shape 3,3 and 413,3 not aligned. So design matrix is 413,3.
Yep.
And our inverse is 3,3.
No.
You do have remote control, so feel free.
I actually gave it up, but okay, just thinking one second.
Yeah.
Okay, design matrix dot t. I'm missing the transpose. Gaurav, I'm missing the transpose.
Where?
Design matrix, the last one.
Here?
Yep.
Okay. There we go. Sweet. Okay, and now we're going to multiply it by the, we're just going to do np dot dot for w, and we're going to multiply it by the x trained x underscore test underscore array.
No, y label.
Y label. So that's
Oops,
going to be
go.
y. Oh, y underscore train dot
ARR.
train dot array, and that's going to give us again a w. So do you want to see that, or
Yeah, we have to.
name
W capital.
w's?
Yeah, W capital.
Okay, there we go. So we got w Test using the testing data set, and make sure you create a design matrix for testing data using same. Oh gosh.
That's the
So
same thing. Just copy paste that code. Create a design matrix underscore test.
do you wanna go ahead? Sorry, I'm bugging you, but like
Sure.
I'm just gonna work on something. You have remote control. Everyone has remote control. Yep.
We are supposed to use, I guess. So in the second part, x underscore test underscore array.
For which I talked to?
For design matrix test np.sum.
Okay. Gaurav, can you scroll down? But you'll have to scroll down one time.
Sure. Here's 13104, 3 not aligned, 3 dimension 1 not equal to 104.
That's why I just realized that. Can you scroll down for the answer
Sure.
ones? Okay.
That's good.
Okay, we just need to make sure that the design matrix was correct. I guess we're done.
That's great.
Can you save this once?
Okay, I'll save. I'm saving this. Can you update everyone's names? That'd be great. They are already in the chat box. There you go. Can you see all this code now? Vineet?
Yep.
We need, I think that we are supposed to multiply by x minus mu. So yeah, so even when using the diagonal covariance matrix, we are supposed to not lose the last part. So like the spread is just the summation j part.
Okay, I am not
I'll,
able to understand, but you can
yeah,
give it a shot.
I'll just share my screen.
Sure, go
Okay.
ahead.
So just save the code that we have, right? Just comment that, and if you're making any changes, just do that right below that, so that we can
No,
go by.
I'm just so yeah, so I'm just showing the like the mathematical part here. So like we have the x minus mu. So this is the density function, but yeah, using the diagonal covariance matrix. So just ignore the denominator
Mhm.
part. So for the x minus mu, so like even if we are using the diagonal covariance matrix, so yeah, they have just replaced it with y vector, and so it will be becoming y1 square. So we are not supposed to lose this last part. So even after inverse,
Okay.
we are supposed to keep this part as well again. So this is the covariance matrix. So just inversing it, and that they have just used here. So the y1, so like y, so we have 2y here, I guess, something. So they are keeping the
Y
y
is
vector
basically
even,
the
and
distance.
yeah, so even if using the diagonal inverse, like covariance matrix inverse, they are still keeping the last part as well.
Mhm. But why would we do that if? Okay, I understand. So the basis function has variances for all three, right? So when creating the first basis function, we're only using the mu from the one, first center. And my question is, why are we using the base variance for all three? Like I understand the math is correct in here, but that's like a doubt of mine now. Can somebody else message me here as well? I have, but can one of you do as well? And can you paste this link in the chat 1 second? One time, Goody.
Yeah, sure.
Okay, it won't let me save the names, Gaurav. You'll have to do it. Gaurav?
Yeah. Can someone just paste like
Yeah, that's what I'm doing. You'll have to do it.
there's already a lot of names here.
If there are, you just go ahead and save it. I'm not able to save it. That's all.
Oh, okay. So we are done, right?
No,
Just save it.
need to be some changes. That's the good link. That's right. Just not able to understand why.
Do you want me to do anything else?
We'll need help. I'm just waiting on him.
Okay. I don't think anybody. We need. Do you know if we are done or?
No, we're not. Like, there seems to be an error. I'm not sure. I guess he's busy.
Everyone is starting to go. We need. Do you think we should end the session? Like, I don't know. Do you know what's the trouble right now?
Yeah, multiplying it with the covariance. So if somebody has to leave, like if they have a time foundation, they can go, I guess. So I guess I'm here now for some
Okay,
time.
got you. Okay. So I have another submission, so I'm gonna start working on that. See you.
Yeah. Bye, Gaurav.
Bye bye. Bye. Vinny.
So Vineet, can you share your screen or?
Actually, my system will freeze, man.
Acha. So should I share?
Sure.
Yeah. So what should we change here?
I'm not sure of that. Gulin, if you have idea of the code, can you start making those changes?
Yeah, I think we just need to multiply it again by. You can just use the first equation, whatever we were using.
First equation.
Yeah, the one commented that is commented. Yeah, design matrix.
Okay.
That's the same one actually. There isn't any change.
Yeah, we need to multiply the last part. I think again with this x underscore train underscore array.
So we need to do dot product. One second. This mu transpose and so within the formula is x minus mu transpose into covariance matrix, right?
Yeah, seems so. X minus mu will give you 10 columns. And if I compute the distance first, this will give me one column. So how do we divide it by the covariance of 3? This covariance matrix is 3 cross 3.
So once can you explain with this line like what this is doing exactly? This line, design matrix.
Which one?
Yeah, this line, design matrix colon comma I.
Okay. So X train has 10 columns, right? We're subtracting the mean for the first center by all the columns, then calculating the Euclidean distance, like squaring it up, summing it up, then taking the square root.
Mm-hmm.
Basically, x2 minus x1 square plus y2 minus y1 square divided under root.
Mm-hmm.
So doing that and then multiplying it with the covariance. But I don't think that's right. Yeah, but don't know how to implement the other part either.
So Gurleen, what do you suggest here? So Vineet, why don't we ask this in TA hours? Like, I'm not sure on this solution.
Yeah, just waiting a couple of minutes. If he doesn't answer, then yeah, I'll ask him in TARs tomorrow.
Okay,
Just wait till 6. If not, then we'll just save it and leave it.
sure.
Gulin, are you there?
Yeah. Yeah.
Yeah, okay. So I was checking the math for multivariate Gaussian distribution. So it does say that x minus mu divided by the standard deviation of that particular random variable, right? So it's doing if there are like four random variables x1, x2, x3, x4, it's doing x1 minus mu squared divided by the standard deviation for that, right? But if you look at how he's calculating bias variance, how he has calculated bias variance, right? Scroll down a little.
Scroll down. Yeah, this is the
Yeah.
formula, right, for the function, basis function.
Yeah. I'm just trying to look at how he's calculated basis variance at the bottom. Okay. Yep. Little above. Go up a little. Yeah, that's fine. That's fine. Okay. So step 5, line number when it starts basis underscore variance. Okay. So first he calculates distances, right? That the model is giving him. So the distance basically, I guess, means is the distance of that point from the center, right?
Yeah.
Now that is ideally x minus mu.
Yeah.
So
He
the
said we
distance,
could. Yeah. He said we could use that.
or
But
directly, or compute it ourselves. Yep. Okay.
yeah.
So now the way he's calculating basis variance is he's adding up all of them for that particular label. For example, if it's the first center, he's adding up all the distances, x minus mu's for all that, and then dividing it by the total number of non-zero elements. That he has basically calculated one standard deviation for that entire center multivariate Gaussian distribution. For 10 variables, he's calculated one standard deviation, right? So ideally, I'm not sure if we can do that and directly multiply it by one. Because if we wanted to multiply the entire covariance matrix, right, the way you said, we would need 10 covariance matrix elements. So we would need a 10 cross 10 for that. And we're not multiplying it with x minus mu because he's already calculating that from x minus mu. That is distance. So maybe what we've done is right, or maybe we're missing something out. Does that make sense?
Yep.
You're
All
aligned, right? Do
depends.
you have any more?
Yeah.
Okay. Mike, did you follow?
Yeah, I followed it.
Yep. Shilling is also here. So, any questions, Shilling? I'm not sure if I'm saying it right, but
All right,
Yeah.
guys, what's
He's here.
happening here?
I'm here.
What is up?
Okay. So we did calculate the design matrix, but we're not sure if it's the correct one. We have some questions based on what we read about Gaussian variations, multivariate, and what we did here. So first we tried to calculate the distance of the point from the mean. So what I did was I subtracted x train with the basis means for that particular I.
Mhm,
I squared it, summed it,
mhm.
and then took the
Okay.
square root. That's the Euclidean distance.
Okay. Wow.
Okay, then took the inverse, multiplied it with the inverse for that particular one,
Okay.
and then took the exponent. Is that correct?
That's fine.
Okay, so one question that we have is that while reading the maths for Gaussian variations, so it says that every random variable will have a standard deviation of its own. So for
Yes.
example, if we have 10 features and we're doing
Yes.
like x train minus basis means, so ideally inverse should be a 10 cross 10 matrix computed from this x train minus means
Yes.
and then correspondingly dividing it. So right
Yes.
now we just computed one standard deviation for all those 10 variables.
Oh no, right? You have three, right? Inverse I comma I. So you have 1 comma 1, 2 comma 2, 3 comma 3.
But that's the standard deviation. Okay, so basically you split all the data into 3 clusters, right?
Yes. Yes.
And all the clusters have 10 features. So what you've
Yes.
computed here is the standard deviation of first cluster, standard deviation of second cluster, but for all 10 events.
Variance you mean. Okay, so if you invert it, okay. Yep.
Yeah, so basically variance for all 10 features for a particular cluster.
No. So variance is not for feature, it's for a cluster of data points. So variance is not calculated using, you know, features. It's not for feature.
Okay. I
So
thought it
consider,
would be calculated for a random variable like x1, x2, x3, x4.
so
up to-
variance, how it, so you calculate, variance is a scalar value, okay? So consider that you first do clustering, okay? We need, you
Okay.
cluster, you get 3 clusters, okay?
Okay.
Every cluster will have, let's say, n number of data points. Let's, you go to cluster 1, you calculate its mean, okay? Using the
Okay.
the data points in cluster 1 and the mean of cluster 1, you calculate one scalar variance. And how do you
Okay.
calculate that is x1 minus mu1, then sum all the elements there and take the square and then divide it by the number of,
Data points.
correct. And that's how, if you carefully look up above,
Yeah, I did see that. Yep.
and Vineet, you were absolutely correct that you could use distances. If you go up,
Mm-hmm.
you see the distances, could have simply used that as well, Vineet, for calculating x minus mu. Once you have x minus mu,
Yep.
you, what you have done, Vineet, is used for loops, right? And I don't like using for loops when you can use matrix.
Yeah, exactly. So I was just
So
trying to do it one by one, but yeah.
it's pretty tedious to do it with for loop one, and secondly, it's time consuming, right? When you can,
Agreed. That's the only downfall for using for loops. Yep.
you should always use vectorized approach, right? So one approach that I would recommend you to is use
Mm-hmm.
distances. Okay, we already have x minus mu in that distances variable. If you go up,
Okay.
x minus mu is already given to you, which is distances. So when
Yep.
you do model.fit transform, you already know, Vineet, that you basically get distances of every data point with respect to the mu1, mu2, and mu3. That's the
Mm-hmm.
meaning of distances. Okay.
Yep.
So when you do model.fit transform for mini batch K, means you'll get a matrix distances, which is n cross 3. Okay, n being the number of instances. So what you have to do is simply you have to matrix multiply this distances variable with the inverse of the variance matrix, which is the covariance matrix. Okay, and then you have to do an element wise multiplication with again distances. That's it. That's the one line solution to design matrix,
Why are you multiplying it for the distances one more time?
because it's x minus mu transpose times covariance inverse times x minus mu. So the equation of Gaussian function is basically an x minus mu square, right? So you have to multiply it twice.
Oh, okay.
Okay.
Or we could just square the distance first and then just do
Yeah.
the dot product. No?
Anything is fine. Anything is
Okay.
fine. Yep.
Okay.
Makes sense.
Okay. That makes sense. Yep. Yeah.
Okay.
And the
Vinit.
distance is just the Euclidean distance, right?
Oh, distances. Oh no, Euclidean meaning it's x minus mu. It's not x minus. Let
It's a
me
data
think.
point, right?
Let me think. Okay, I am not sure about that, Vinit. So I shouldn't tell you that what
Okay.
exactly that is. But you can research about it about when you open sklearn's library. Okay. So I'm not really sure, but you can
Mm-hmm.
simply take L1 loss or L2 loss. Sorry, L1 distance or L2 distance. Anything is fine. Okay.
Okay. Okay.
All
Okay.
right.
That makes sense.
I think that's it, right? There's nothing more to do after that.
Yeah. No. Nothing more.
All
So we
right.
can just save it and quit, right?
Yep. Thank
Okay.
you, Vinay.
Thanks.
Thank you, Mayank. Thank you, everyone who participated.
Thanks, Mihir, for the help.
Sorry for
Thanks.
it being
Thanks.
too long.
No, we
Yep.
understand. Like this was complex conceptually.
Okay. All right. Okay.
Okay.
Mhm.
Okay. Have a good day, guys, or night, whatever it is.
Mhm.
Bye.
Okay, bye.
Bye.
Bye, Gurleen.
Bye.